Hey guys, today I'm going to be showing you all how Eratosthenes calculated the circumference of the Earth. One thing before we get started, I wanted to tell you all that Eratosthenes was the head librarian for the Great Library. That great library was located in Alexandria, Egypt. Now, I don't know if you guys can see it, but Alexandria is located right up here. That's where it is in Egypt, and so that's where he worked. But he was born in Greece, and here's a picture of um him, I guess. All right, so there's the picture of Eratosthenes here. That was him. Um, Anyways, that's Eratosthenes right there. He spent most of his time in the library, which I think is pretty cool, and is one of the reasons why he's so smart. Anyways, yeah, Eratosthenes was Greek, but he lived in Egypt, head librarian. He was born 276 BC in a place today known as Libya, and sadly, as all great men do, he died in 194 BC in Egypt, Alexandria to be exact. So that's that. Alright, so in this video I'm going to show you all how exactly Eratosthenes did his calculations. You see there was a town called Syene, also known as today, it's called Aswan. It's located right there. And what Eratosthenes did is he knew that the distance from Aswan to Alexandria up here is 23.5 degrees on the Earth's surface. So, using that, what he did was, since he knew that 23.5 degrees was the north latitude from Alexandria to Aswan. By the way, north latitude is, here, let me show you something like this. Alright, so picture it like this. You have the Earth right here, then you have Syene on the equator, which is horizontal. It's on the equator, which means horizontally connected to the center of the Earth, and we have Alexandria up here, 23.5 degrees north latitude of Syene. So what that meant to him is, since it was 23.5 degrees, he also knew at the time, due to because of all the great philosophers and astronomers back then, that so he knew that that was 23.5 degrees, and he also knew that Earth on its Earth on its axis is tilted 23.5 degrees as well. So that may not look 23.5 degrees, but if it was pointing straight up like that, the distance between these two is also 23.5 degrees, which we can run here to there, even though it may not look it. But, so since he knew that, that also meant that so that also meant that one day when the Earth was rotating around the sun, one day every year, the longest day of the year, the sun over here, whoa, the sun over here the rays from the sun would shine directly into a well in Syene. and it would shine also on Alexandria. So when the rays shined on Syene into this well, Eratosthenes kind of figured, if I planted a pole in Syene and I planted a pole in Alexandria, the shadows would be different because the sun rays, because we're a curved planet. On the outside we're a sphere, that the shadows wouldn't be the same. Enough of that. What he did was he was trying to prove that the pole. He was trying to prove that the pole in Syene, the pole right here, when it lines up on that one day a year, it would take this ray of sunlight, go into the well, and cross and follow it into the earth, if it could travel through the earth, and it would go right to the center of the earth. This sun ray in Syene go to the center of the earth. But the one in Alexandria, the sun's rays would completely miss the center of the earth, like that. Now what we know from geometry is that this line right here is the transversal of these two parallel lines. So those two lines would be kind of parallel. I have no idea what just happened. That's that. That's great. Anyways, imagine these two are parallel. They have the parallel markings. This would be the transversal. Now what that means is that would mean that this angle right here, that angle right there, the 1, 2, that angle right there, but shown by this line and that line, would be congruent to the angle right here and right here. Oh, the angle right there and right there, or this angle right here is being circled. So this angle would be congruent to that angle. So what he did is he went up to Alexandria, he took his protractor, or something along the lines of that, and he measured what the angle was, and it ended up being 7.2, or yeah, I think it was 7.2. Yep, it was 7.2 degrees. So what he did from that point on is he knew that, alright, so he found 1 degree of the Earth. Since this Earth is a circle, he did 360 over 7.2, and he got 50. So what he knew from there, alright, so he had 50. He knew that the sum of it was 50. And that means that 7.2 was 1/50th of the circumference of the Earth. So what he did, again, is he measured the distance from Syene, marked by this kind of Sion line. He measured the distance from Alexandria to Syene to find that it was 5,000 stadia at the time, or stadiums was the measurement note over there, but which converts into about 500 miles in the US system. So we got 500 miles was the distance from Alexandria to Syene, which means he multiplied that number by the 50 over here. I don't know if you can actually see that, but I'm just gonna, he got 50 over here, but he multiplied that by 50 and got 25,000 miles for the circumference of the Earth. So let's just recap what he did, just for clarity, just to make sure you guys know what's going on. So he planted a pole right here in Alexandria, pointing straight up, planted a pole in Syene, planted straight up, obviously not that far. But what he did then is he waited for that one day in the middle of the summer, longest day, for the sun rays to fill that well in Syene, and the sun ray went like that up there, and when it hit Alexandria, it went like that. But the pole that he stuck in Alexandria straight up is actually kind of tilted when you look at it like this, but it would be tilted straight to the center of the Earth. So that pole that he planted in Alexandria would be the transversal of the two rays of sun. If you could see me in real life, I'm doing all these crazy hand motions. Anyways, then he measured the interior angle over here and knew that it would be congruent to this angle over here, which is 1/360th. It'd be 1% of the Earth. It'd be 1% of the whole circle of the Earth. Obviously, it doesn't really show like that in the diagram, but it's exaggerated. So that would be 1% of the Earth. So what he did is he measured that. He got 7.2 degrees for right here. Yeah, he got 7.2. And what he did from there is he did 360 over 7.2, and he got 50, which would mean 50 miles, 50 stadia, whatever he did. That would be 50, and he'd have to multiply that. He'd have to multiply the 7.2 by the 50. No, he didn't actually. Scratch that. What he did is he got 7.2 over here. Right? He kept it. He's like, I'm good with that. He measured the distance from Alexandria to Syene. He got 500 miles, or 5,000 stadia. So that's what he got there. Then what he did is he took the 50, because he concluded, transversal and stuff. He took the 50, multiplied it by the distance between Alexandria and Syene, the two rays of sun, measured that, times it by 50, and he got, I'll put it on the screen real quick, he got 25,000 miles using just basic tools. Now what the actual circumference around the Earth is, well, I mean, since the Earth is not really perfectly round, we can never know. But other scientists more recently have gotten the most accurate so far is 24,900 miles. So in perspective, he was not that far off. He was 100 miles off, and that was 2,200 years ago almost. This guy is a genius of his time, yo. Anyways, hopefully that made sense. That's the end of the video, so, enjoy your day. Stuff like that, You can never have too much applesauce. Good night.